Hello everyone! Today we are doing lesson 3-4 and our learning target is going to be I can write a proof with perpendicular lines. Alright, moving on here. So we have a runner here that's going to the finish line. So let's think of this runner as a point. So we have a point here and going to the finish line. So what is the shortest distance from that point to the finish line? And I know from a few years of experience what kids typically say. And kids typically say that what we need is a straight line. Okay, so we need a straight line. That's what kids typically say. So I'm going to draw in a straight line from this point to the finish line. So that is a straight line. This is a straight line. This is a straight line. Is one of those paths better than the other paths? And if so, why? And which one's better? So I bet after you're thinking about this, you're like, oh, it can't be just a straight line. It has to be the fact that it is the line that is perpendicular to the straight line. So it's a line that goes through the point that goes perpendicular to the straight line. That is going to be your shortest distance from a point to a line. So the distance from a point to a line, distance, and whenever they say what is the distance, they always mean the shortest distance. So remember, mathematicians are efficient, and they don't say the shortest. When they say the distance, they want to know the shortest distance. So the length of the perpendicular segment from the point to the line. So it has to be perpendicular. This would be the shortest, not this, because that's still straight. This is still straight. Okay, we want the shortest, so we want the one that comes down perpendicular. Okay, find the distance from point E to FH. So we want the one that comes down perpendicular. So we're going to say EG. Now, if they actually want you to find the distance, remember you'd be using that distance formula that we've already talked about before, so that it is x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Okay, and remember the order of these numbers doesn't matter, because if we do 5 minus 2 and square it, or we do 2 minus 5 and square it, because of the squared, it's not going to make a difference. All right, which is the shortest path from line A to line M? Well, of these here, it's going to be AD, because it looks like that one is going to be the perpendicular. So AD would be the shortest path. So perpendicular bisectors, it's going to divide the segment into two equal parts, which means that it must pass through this midpoint of M, and it forms a right angle. So we did some back in, I don't know if it was lesson 1-2 or something, and if we had JK here, and we had this coming through so that these two were marked congruent, we just had a segment coming through. This point or spot still can mark so that we have a bisector here, but notice we have a word in front of it that is saying perpendicular bisector. So this one's still a bisector. It's still dividing it in two. It's just not coming down perpendicular. So true or false? M is the perpendicular bisector. What do you think about M? Nope, not a perpendicular bisector. M would be considered the midpoint in this particular case. So M would be the midpoint. All right, line M is the perpendicular bisector. Well, it is definitely bisecting it, but do we know that it's perpendicular or not? No, so we would just say that M is a bisector. We cannot put in the fact that it is a perpendicular bisector because we don't have any markings to show that it is perpendicular. All right, make a conjecture now about G and H. All right, G and H. Well, let's see. This angle 1 and 2 looks like it's a linear pair. So the measure of angle 1 plus the measure of angle 2 has to equal 180. Well, if 1 and 2 are congruent, what is that going to make them both be? So they're both going to have to be 90, which means that line G has to be coming down perpendicular to H. So the conjecture we can make is that G is perpendicular to H. All right, so we have a theorem that's called the linear pair perpendicular theorem. So if two lines intersect to form a linear pair of congruent angles, so 1 and 2 are a linear pair of congruent angles, then the lines are perpendicular. And we call that the linear pair perpendicular theorem. Now, sometimes I have a hard time remembering the linear pair perpendicular theorem, so I just simply say if 1 and 2 are a linear pair, so I kind of just describe it. If two lines intersect to form a linear pair and the angles are congruent, then they must be perpendicular. So sometimes I just don't remember the exact name. I just use words and describe it. All right, what do we have here? H is parallel to K. We know that for sure by looking at the diagram. And we know that J is perpendicular to H. What can we now conclude about J, line J, and K? Is J going to have to be perpendicular to K also? And yes, it is. So in a plane, if a transversal, so J, is perpendicular to one of two parallel lines, so J is perpendicular to H, and H and K are both parallel, what can we now conclude? That J is perpendicular to K, and that's called your perpendicular transversal theorem. All right, what conjecture can we make about M and N? Let's see. If M is perpendicular to P and N is perpendicular to P, do we not have corresponding angles here? So if we have corresponding angles are congruent, what can we conclude about lines M and N? They must be parallel. So this is what we talked about yesterday, and I used the converse of corresponding angles. Okay, so converse of corresponding angles. We have two lines cut by a transversal and corresponding angles are congruent. Therefore, the lines M and N must be parallel. Well, that also works because if they are perpendicular to the same line, then they must be parallel to each other. So if two lines are perpendicular to the same line, then they must be parallel to each other. Okay, that's the line perpendicular to transversal theorem. All right, looks like we are at the end of the lesson for today. So good luck on your homework for lesson 3-4.